All right, so yesterday we learned a couple different rules to differentiate polynomial functions. We learned about the power rule, which was the main one that we were using. We also learned about the constant rule, which is if I take the derivative of a constant, it's equal to 0. And then I kind of threw in a little summary at the end here, where we were looking at the sum rule and the difference rule. So I didn't formally introduce these to you guys, but you guys have been using these kind of all along. So it basically just says, like, if I'm taking the derivative of something that has multiple terms, like this guy, I will take the derivative of each individual term. So we were applying that already when we did the derivative of multi-term expressions or polynomials. So today we're going to take a look at how we can find the derivative of something when it's not in expanded form. So the only way that power rule works is if I have an expression that is all expanded out and has individual terms, right? So I can use and apply the sum and difference rules for those cases. So that's when we can use power rule. Now, if I have the product of two multi-term equations, I can't exactly apply power rule because it needs to be all expanded. So there is one option. I could expand out, and I could try to then apply power rule. But for other things that I can't quite maybe expand out really nicely, product rule works really well for us. So the product rule of two functions that are being multiplied is going to be, so we're going to use a little chant. It's going to be the derivative of what's in the first bracket times the second bracket as it is, plus the first bracket as it is, times the derivative of the second bracket. So we use the little chant, so you're going to remember this in your mind. Derivative of the first times the second, plus the first times the derivative of the second. Okay, so I'm going to show you why this is true, because a lot of times we would think if I have two things being multiplied, why isn't the derivative just f prime times g prime? Why can't I just do the derivative of this and multiply it by the derivative of this? So we're actually going to use Newton Quotient. So that's not true. We're actually going to use Newton Quotient to help us prove this. So like I said, everything in calculus hinges on the Newton Quotient and us being able to create these rules from proving in the Newton Quotient. So let's take a look at the derivative. With respect to x of f at x times g at x. So this is just how we write the derivative of something with respect to x. And we're going to use the Newton Quotient for this. So we're going to use that limit as h approaches 0. And normally what we would have is f at x plus h minus f at x on the top. Now what we're deriving is f at x times g at x. So we're going to have f at x plus h times g at x plus h minus f at x times g at x. Okay, simply because we have f at x times g at x here. Okay, so in order to prove this, we need to do a little fancy move here, and we need to add 0. And you'll see how this kind of helps us once we get to the end here. But what I'm actually going to do is I'm going to add and subtract the same thing. We actually do this in like completing the square and stuff like that, just so that we can work with it a little bit differently. So I'm going to subtract f at x plus h times g at x, and I'm also going to add it. So if I subtract it and I add it, really I'm just adding 0. But then we get to work with this equation a little bit differently. So it helps us prove this. Okay, so what I'm going to focus in on is I'm going to focus in on this first group of terms, and then I'm going to focus on this second group of terms by common factoring something from each. So what's common in the first group of terms? Close. F at x plus h is common, right? So I'm going to take that out of the first set of terms. And I will be left with g at x plus h minus g at x. And second group of terms, what's common there? G at x is common, yep. So we can take that one out. And we are left with f at x plus h minus f at x. Okay, so we can kind of do like a cool little thing with limits. Anytime I'm like adding individual terms in limits or even multiplying terms, I can actually separate those guys out into their own limits. So what I'm going to look at here is separating out this little section with this one. And we know if we're adding two terms that the denominator needs to go with each added term. So I'm going to do one separation here. And that's all going to be over h, and I'm going to separate this out into its own limit as well. Okay, and then I'm going to do it one more time with the multiple between here. Now we know when we're multiplying things that are over a common denominator, only one of those things will take the denominator. Because if I put the denominator in both of those, that means it would be h squared when it multiplies back together. So I'm going to kind of separate like this with this multiple right here. Okay, and we're almost there actually at this point. So I'm going to take the limit as h approaches 0 of f at x, and that will be multiplied by the limit as h approaches 0 of all of this stuff that's left here. And then same thing over here. This will be by itself, and then I'm going to have this whole thing right here. Okay, so this is actually a property of limits, that the limit as we approach like individual added terms can be separated out into their own limits, or even multiples can be separated out into their own limits. Emily.
Why are the first term and the third term, why are they not over each?
Yeah, does somebody know why I didn't put these over h? Essay?
Because when they multiply, it will become h squared, which is not true.
Right, so we want to just maintain that this is still over h, right? So if I were to just multiply this back in, I don't want it to be h squared here.
Oh, okay.
Make sense?
Yeah.
So we have to do that when we're adding two fractions, but not when we're multiplying.
Okay.
Okay, so when we go to evaluate limits, we usually plug in h equals 0. So when I sub in h equals 0 into this, I'm left with just f at x. This whole thing, I'm not going to plug in h equals 0, but this whole thing, do you guys recognize this? That's the original Newton quotient, right? It's like f at x plus h minus f at x over h, and the limit as h approaches 0. So this is actually the derivative notation for the derivative of g at x. So this is actually equal to g prime at x. Okay, that's actually the actual definition of what a derivative is right there. That is the Newton quotient in and of itself. Okay, this guy, if I go to sub in h, there's really no h for me to sub in. That's just g at x. Okay, and this, again, is the Newton quotient, and that means the Newton quotient helps us find equation for slope of the tangent. It finds the derivative for us. So this is the derivative of f at x. And this is why when I do the derivative of f at x times g at x, it's equal to the derivative of the first times the second plus the first times the derivative of the second. Tammy?
On a test, would you ask us to show both?
I'm just showing you guys so you know where some of these derivative rules come from. I'm not going to ask you to reproduce them. So, yeah, I just want you guys to know that the reason why all these derivative rules work and the reason why they are the way they are is because they come from the Newton quotient. Okay? Kaylee? Yep. So that's a good question. Guys, can you listen up at the back there? Say it one more time.
Like the notation dx over dx, like y over dx or something.
So if I say something like d of f at x over dx, let's just say to simplify it a little bit, f at x is really just function notation for y, right? So if I had an equation like f at x equals something or whatever, I could say derivative of f at x with respect to x. When I have y equals, that's why we end up saying dy over dx. So the derivative of the function y with respect to x. Just means like we're differentiating the independent variable. So we're differentiating with respect to the x value, or x variable, I should say. Okay, so this really just means derivative with respect to x, d over dx. Okay, now let's use the product rule. Okay, so we're going to use this chant in our heads. Use it as you're going here. This is going to be the first, and this is going to be the second. So when I do p prime at x, I'm going to do the derivative of the first. What's the derivative of 3x minus 5? Grayson? It's just 3. Times the second, exactly as it is, plus the first, exactly as it is, times the derivative of the second. What's the derivative of x squared plus 1? 2x. Okay? And then to get this into simplified form, we're just going to expand and simplify. So I'm going to bring the 3 in, bring the 2x in, and then we'll gather like terms. Okay? So everything beyond this is like not calculus stuff. It's just simplifying stuff. Okay, and then you're just going to simplify. And that's our derivative.
Do we have to write out the p and the s like in?
As long as you put it up here, you're fine. Okay, sometimes you might be able to factor a quadratic. Factored form is simplest form, so I would encourage you, if you notice that you can factor your quadratic, factor. Okay, this one's not factorable. Okay, second one. So this is going to be our first. This is going to be our second. Because this is y, we're going to use that dy over dx notation. Okay, derivative of the first, which is 2, times the second, exactly as it is, plus the first as it is, times derivative of the second, which is negative 1. Okay, and then just expand and simplify.
Would you recommend that we factor if we could, or do we just leave it as is?
Yeah, I mean, this one technically we could factor out a negative. I think either one of those is fine with me, but you're right. Technically, we could go a step further with this guy and just do like this. Okay, I won't be like super picky about this, but sometimes you'll notice we'll do some examples where like common factoring allows us to reduce further, and those would be the cases where we would definitely want to do that. Okay? Any questions on those two so far? Okay, so you can see how our stuff from yesterday is kind of coming into play here, right? We have to use power rule as we're doing this. All right, so in example 2, we actually have a product of 3 different things. So there's a couple ways that we can do this. We can technically do, if I have like a first times the second times a third, I can do derivative of the first times the second times the third plus the first times the derivative of the second times the third plus the first times the second times the derivative of the third. Okay, we could do that. That is an option. You will get the same answer a couple different ways. Essay?
Can you do that from like bigger numbers, like for 5 brackets? Would that?
Yeah, so you would do derivative of the first times the second, third, fourth, fifth, and then so on. You'll just have a bunch of terms. Now, I think that we could just do, like if I distribute this 2x in here, I think we could just do that and then apply product rule as we're used to. Okay, so either option. Pardon? Yeah, you can do it the other way. So if you want to try out this, you can try that out and see if you get the same answer as us doing this one. Grayston?
How do you know which one to distribute?
I mean, you could distribute any one of the,
3?
like to one out of the 3, yeah. So if you wanted, you could have put the 2x in here instead.
But it has to be a single bracket that's a single number.
So if it were 3 brackets that have like 2 terms in each in them, you'd have to FOIL one of them. Yeah. So in that case, maybe this way would be the better way to go. Okay, so let's do g prime at x. I'm going to work off of this. And we're going to do derivative of the first. So this will be our first, and this will be our second. Derivative of the first is 4x minus 2 times the second plus the first times derivative of the second. Okay, and expand and simplify. So we're going to FOIL this guy and then just distribute the 2x in the second one. Oh, that's 4x cubed. And this asks us to find g prime at -1. So what is the slope of the tangent when x equals -1? So we'll just take an extra little step here and evaluate g prime at -1. So what's that, -32, I think? Any questions on that one? Okay, so usually a question I get every time we do this is, okay, so we're doing product rule for something like 2x plus 3 and 1 minus x. Can't I just do 2x minus 3 and 1 minus x and just FOIL that and use power rule? Couldn't I? I totally could. I could do 2 times x and then just expand this out. I could simplify. And then, isn't that easy to differentiate? I could just do power rule now. Certainly, you can absolutely do that. The reason why product rule is important is because if I were to try to do something like this, the derivative of something that I can't necessarily FOIL out, then I have to use product rule. Now this guy, we need another rule in order to actually use product rule with that, so I can't quite show you guys that one yet because we need a little bit more information. But This is why we have product rule, is because of situations like this. Okay, so we're going to practice it without foiling out first, just so that we can get the hang of product rule. Okay, so determine an equation for the tangent. So when we think equation, we want to think equation of the tangent line in y equals mx plus b form. To the curve of this function at x equals 2. So when we think slope of the tangent, we want to think derivative. So we need to start by finding the derivative of the function. Think of this as your first and as your second. Does someone want to try the derivative for this one?
What was the answer?
Negative 32. Anyone want to try the derivative here?
Is it plus 2x?
For this guy? Yep. So what's the full derivative of the function though, using product rule?
Oh, then it's just x squared minus 2x plus 1.
Mm-hmm. And then plus?
Plus 2x.
So derivative of the first times the second plus
I don't know.
the first as it is, right? Times derivative of the second. You want to do derivative of the second for us?
Oh, okay, so then 2x and then minus 2. Okay, yeah.
Great, yeah. So I could spend a bunch of time expanding this out and simplifying, but it doesn't really ask us just to find the derivative. We're using the derivative to help us with something else. So I think rather than expanding and simplifying, let's just calculate the slope of the tangent when x equals 2. I'm just going to plug in right away here. Okay, so we're going to evaluate dy over dx, or slope of the tangent, when x equals 2. So you're just subbing that in for all the x's above. If you want to simplify out first, you can definitely do that. But if you're just using it to calculate something else, I feel like we can just input it. Okay, unless you feel like you're going to get confused by doing that. Okay, so we just found, so we know so far, that the slope of the tangent line when x equals 2 is y equals 10x plus b, and we need to find the b. So we did a question like this yesterday. What do we need in order to find the y-intercept of that line, or the b value? Kaylee?
The xy point.
The xy point, and how do we find that?
The original.
Yep.
Plug in x for 2.
Perfect. So in the original equation, in order to find a point on the tangent, Nicole, stop. Okay, in order to find a point on the tangent, it's the point that the tangent line and the function share. So we can actually use the function to help us with that. We're going to plug that x equals 2 into the original function, and then just calculate here. So I think we get 3 times 1, so we get 3. So this is our point on the tangent line, and I can sub that in for x and y to isolate for b. And then just sub that back into your equation for your tangent. Okay, any questions on that one? Okay, so if I'm trying to find the equation of a tangent line, I find the derivative to get the slope of the tangent. I need a point on the tangent line, which I can get from the original function, and then I plug that into my y equals mx plus b in order to solve for b. Okay, so kind of just like a three-step process. Find the derivative, evaluate it at whatever x value, find the point where x equals whatever value it's given you, and then plug it into your y equals mx plus b equation. Can I scroll? Okay. Last one for today. This is a business application. So we actually can use calculus in business to find certain maximums of revenue and things like that. So our example for today is student council is organizing an annual trip to an out-of-town concert. For the past 3 years, the cost of the trip has been $140 per person. At this price, all 200 seats on the train were filled. This year, Student Council plans to increase the price of the trip. Based on a student survey, the council estimates that for every $10 increase in price, 5 fewer students will attend the concert. Write an equation for revenue, and then we're going to see how calculus can help us determine what the optimal price is for them to sell these tickets to the concert. Okay, so business people out there, how do I find revenue? Sorry? Okay, price times, in this case, this is going to be number of tickets sold, right? Okay, and this is based on the number of $10 increases. So my price, we're going to call this R at n, our function. So revenue based on number of price increases n. So R at n is going to be equal to, normally they're selling for $140. So anything to do with price is what we're going to put in this first bracket. So 140, and we're doing $10 increases in price. So we are going to add $10 a certain number of times. So depending on how many times we increase, that's the number of $10 increases that we'll do. So that will be times n. Okay, and then the number of tickets sold. So initially, when the price was 140, it was 200 tickets that were being sold. Now, what's going to happen with every $10 increase that I do? Is it 1?
5.
Oh, 5 fewer students. Okay, so every single time I increase the price, 5 students will go down. So n is the number of price increases, right? So if I increase the price twice, then 10 students. We'll have 10 less students. So this is our revenue function here. Okay, the second part of this asks us to determine when r prime at n equals 0, and it asks us to interpret what that gives us. So firstly, we need to find r prime at n. We're going to use product rule for this, although again, we could expand if we wanted to and use power rule, but this is our new rule, so we're going to practice it. Think of this as your first and think of this as your second. Someone want to do the derivative for the revenue function here? Nicole? Pardon? So, derivative of the revenue function first.
Oh, 10,
Yep.
-5.
So derivative of the first times the second. So times 200 minus 5n. Plus, Kaylin, can you finish?
140 plus 10n
Mm-hmm.
minus 5.
Perfect. Okay, plus the first times derivative of the second. Okay, excuse me. Okay, so we want to know when r prime at n is equal to 0. So I think we are actually going to have to expand and simplify this one just so that we can solve for n. So we're solving for where revenue, the derivative of revenue is equal to 0. Okay. And we're just going to isolate for n here. Move the 1,300 over, divide out the 100. And we get n equals 13. So when the tangent line equals 0, that's what we just figured out, right? We found the tangent, or equation of the tangent, and we set the slope for that equation, for the slope of the tangent, or the derivative, in other words, equal to 0. What this is giving us is actually the part of this function where the tangent line is horizontal. And that's actually going to be, for this particular scenario, this is a quadratic that opens down. It's actually going to be the maximum of the revenue function. So what we just found is that for 13, I think it was $10 increases, right? So for 13 $10 increases, or in other words, an increase of $130, let's just say student council will maximize their revenue. Okay, so when we set the derivative equal to 0 and we solve for that, that's actually going to give us locations of maximums and minimums of the function. Now in this case we just have a maximum, but it's going to give us maxes and mins depending on where those turning points are. Okay, and we can actually figure out what that maximum revenue even is. We can sub in our at 13 into the original function and just calculate to find the maximum revenue. So we could do 140 plus 10 times 130, or sorry, 13. And then 200 minus 5 times 130, or sorry, 13. I keep saying 130. So their revenue will actually be $36,450. Now they also have to pay, obviously, for accommodations and traveling and the concert tickets and stuff like that. So not all of that they'll get to keep, but that's where they're going to maximize that return. So they will sell tickets for $270. They're going to sell 135 of them. That would be what's projected based on the number of price increases. So I guess I can just say they will sell 135 tickets for $270, giving a revenue of $36,450. Oops. Okay. We'll pause this or